Here, let me close my door and then we can get started.
Okay, Kat, what are you doing?
Okay, guys. So today we're going to take our first sort of step away from power series, which I imagine will be a relief for most of us. If, however, there are any particular problems that you guys want to see, we can take a look at one or two homework type problems before class moves away from that material. So let's do it like this. If there's anything from the current or last homework, which was extended till today, that you guys would like to take a quick look at before we move on and move away from power series, let me know and type it into the chat there, and we can talk about one or two of those before we start talking about section 8.1, which is where we'll be going today. Not like I didn't know. Well, I'll get my dot cam fired up here. In the meantime. Okay. Yeah, number 20 from homework 11, we can certainly do that. Were there any others from the homework? So study guide 1, yeah, so I did go back and grade everything old. So if you handed in study guide 1, you should have a grade for study guide 1, regardless of when you handed it in. Same is true for study guide 2. So all the study guide grades should be in. If you're missing a grade on something, then please send me a Canvas message or an email letting me know. Let me know what is missing and when and where you submitted it if you have, or if you haven't submitted it, go ahead and please submit it and then send me that Canvas message letting me know where. But yeah, if you submitted the first study guide and you did not get a grade for it, that just means I missed something when I went through and did my gradebook cleanup over the last couple days. If there aren't other homework problems, I will go ahead and get started on this. So you want to see homework 11, number 20. Let's do it. Oh yeah, okay. So use McLaurin series. One over the 10th root of e, correct to 5 decimal places. So this problem is a little bit involved in that we really have to do two things. We have to figure out the Maclaurin series that is useful here and then plug in some number. And then we need to use some sort of estimation theorem. And the only estimation theorem I've required you guys to actually learn is the one for alternating series. Although there is a separate estimation theorem for Taylor and Maclaurin series. So if you've been having problems with this one, it might be because they're anticipating you to use a separate theorem from the one that we have learned. But the core of the problem is definitely worth looking at. It's a good problem here. So let's get started. 1 over the 10th root of e, that's e raised to the power of negative 1 over 10. And we know that e to the x is sigma n from 0 to infinity, x to the n over n factorial. This has IOC, negative infinity to infinity. So we can plug any number from the IOC into this series, and it will converge to e to that number. Specifically, e to the negative 1/10 is going to be the sum from 0 to infinity, negative 1/10 to the n over n factorial. And this can be cleaned up quite a bit algebraically as negative 1 to the n over 10 to the n times n factorial, which is an alternating series. Now I think the values you get out of the estimation theorem for alternating series are the same as the values you should get out of the Taylor inequality. Taylor's inequality isn't something that we teach in the non-honors version of Calc 2 here. Sometimes we'll talk about it a little bit, but most of the time I find that it just serves to confuse people. So because it's no stronger than our existing estimation theorem, we'll use our existing estimation theorem. The bn's here are 1 over 10 to the n times n factorial. And the trick is figuring out what we need the error to be to get this accurate to 5 decimal places. So we want s, which is sigma n from 0 to infinity, negative 1 to the n over 10 to the n times n factorial, estimated accurate to 5 decimals, i.e., we want the error less than 0.0. That would guarantee that our first decimal is correct, second decimal is correct, third decimal is correct, fourth decimal is correct, fifth decimal is correct. And then we need the error in the 6th decimal to be small enough that it can't fuck up rounding. If we make this a 1, then that should do it. But you can imagine a situation where the first 5 decimals were correct, and then the last decimal was like a 5. And so if we're off by a 1 here, that would have us round up 1 here. But this should be sufficient. It might be a little bit overkill, but it should be sufficient. As long as we don't round. Now, what is this number? This is 10 to the negative 1, 2, 3, 4, 5, 6. So we want our error to be less than 10 to the negative 6. And according to the estimation theorem, for alternating series, from section 11.5, this will be true given that b sub n plus 1 is less than this number, 10 to the negative 6. So this is where we're at. And then b sub that n, whatever the smallest n is, which satisfies this inequality, would be that n is the number of terms in the partial sum you need to get the desired accuracy. So let's take a look. Let's unpack this inequality. Let's write it out. B sub n plus 1 that's 1 over 10 to the n plus 1 times n plus 1 factorial. And we want this less than 1 over 10 to the 6. And this is one of those things where maybe we can do a little bit of direct work, maybe not. The factorial here is going to mess things up. So probably my move would be to guess and see if there's any guesswork that we can do. It's true that if n is bigger than 5, this will automatically be true, because just the 1 over 10 to the n plus 1 will be smaller than this. But the n plus 1 factorial actually grows way faster than 10 to the n plus 1. So n equals 5 is overkill. So let's guess. Let's try capital N equals 2, just for fun. That would be 1 over 10 to the 3 times 3 factorial. I'll employ my buddy Desmos here. So this is 0.0001. 3 factorial is just 6. So this is 1 over 0.006, which is not small enough. 10 to the negative 6 is 0.000. I'm taking 1, 2, 3, 4, 5, 6. So this guy is 0.0016 repeating. 2 zeros? Yeah, 3 zeros. And this is not yet smaller than this. If n is equal to 3, then we'll have 1 over 10 to the 4 times 4 factorial. Which is starting to get there. So that's 0.1, 2, 3, 4, 5, 4, 1, 6, 6, 6. And remember what we're trying to do. We're trying to find something here that is smaller than this guy, 0.1, 2, 3, 4, 5, 6, 10 to the negative 6. So what is this? This is 0. We've got 1, 2, 3, 4, 5. And then in the 6th place here, we have a 4. So n equals 3 isn't going to do it because this is bigger than a 1. This might be enough to get the desired accuracy. But if we really want to be safe, we should go one more until that inequality is satisfied. So when n is equal to 4, this would be 1 over 10 to the 5 times 5 factorial. Let's see what that is. Yeah, this is plenty small. So this guy is 8.3 times 10 to the negative 8, which is certainly smaller than 10 to the negative 6. So n equals 4 is more than enough. N equals 3 might be enough. But remember what our goal is. So, we want to calculate e to the negative 1/10 this should be approximately equal to the sum from n equals 0 to, I'll go ahead and use the 4 because we know it's safe, negative 1 to the n over 10 to the n times n factorial. Now the summed from 0 to 4, rather than going all the way out to infinity. And this I can write out just to give us a feel for what's going on. Negative 1 to the 0 over 10 to the 0 times 0 factorial, that's 1. And then we'll have minus 1/10 times 1 factorial, and then plus 1 over 10 squared times 2 factorial, and minus 1 over 10 cubed times 3 factorial. That's out to the n equals 3, so 1 more plus 1 over 10 to the 4 times 4 factorial. This is the partial sum I need to calculate. And there's no sense in doing this by hand. You're free to use a computer to do this. Let's talk to Wolfram for a minute. It's a little better at these sums. So you can say I want to sum negative 1 to the n over n to the n times n factorial from n equals 0 to n equals 4. Let me check and make sure it looks how it should. It does. We get this, 72,387 divided by 80,000, which we could ask for as a decimal. It's 0.9048375. So how many decimal places do you have here? 1, 2, 3, 4, 5. So we're wondering, is this correct out to the 3? Are these first 5 decimal places? 1, 2, 3, 4, 5. Yeah, are these first 5 decimal places correct? We can ask Wolfram or Desmos or whatever for the exact value of e to the negative 1/10. Get e to the negative 1/10 from Desmos is equal to 0.9048374, blah, 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 blah. So our fourth partial sum, which written out looks like this, has this decimal. The first 5 places of which are this. The actual value of e to the negative 1/10 has a decimal that starts like this. And yeah, the first 5 decimal places do match. 0.90483, 0.90483. So your answer there is just going to be 0.90483. Those are the first 5 decimal places of e to the negative 1/10. And we did it as the problem asked us to do it, by using an appropriate partial sum, the partial sum that we determined using our estimation theorem. So this is a good problem, right? They just want us to give them the value of this thing accurate to 5 decimal places. Of course, you can cheat this, right? Just like feed it this number. But the whole point is to see this theorem in action. So you come up with your series representation for this number by plugging negative 1/10 into the series for e to the x. Then you use the estimation theorem for alternating series to figure out how many terms of that series you need in order to get the desired accuracy. Questions on this? Comments, concerns, any part of this that you guys would like to look at more carefully? Okay. Then we're going to change gear. Surface areas, we're going to talk about arc length and surface areas. Usually when I introduce this material, I do it by first introducing parametric curves, because I feel like in the setting of parametric curves, it's a little bit more natural. But we're going to try something different this semester. We're going to go back and try to work this in the situation where we're dealing with a function first. And then we'll move everything over into parametric land when we get to talking about parametric and polar curves. So congratulations, all the series stuff is over. I promise. Even power series. You're done. It's over. The material that we're going to move on to isn't super hard. So we've been in chapter 11 here, and we're going to spend time this semester in two other places. We're going to go to chapter 8 and chapter 10. Now, like I said, normally I would come to this place at this point and introduce arc length and surface area in the setting of parametric curves. But we can come back to 8.1 and 8.2 and look a little bit at how to solve those problems in the setting where you're more familiar. I think that the formulas in the chapter 8 setting are a little less intuitive, but maybe being in a place where you don't have to learn about parametric curves at the same time will make it a bit easier. So I want to come in and cook up these concepts of arc length and surface area for you, and then we're going to move to chapter 10. So we'll do 8.1 and 8.2, and then we're going to do 10.1 through 10.4. And those are the last sections in the course, ladies and gentlemen. That will be the end of Calc 2. So again, breathe a deep sigh of relief. Your long, hard night is over. There is no more series content in this class, besides, of course, what you'll need to use on the final and on exam 3. So now we move to applications. There may be a problem or two where I say, oh, and to solve this problem well, you would need to use a series. You would need to use a power series or something like that. But I won't browbeat you with the stuff. First, arc length. Arc length is what it sounds like. I hand you a curve. So this is arc length section 8.1, and surface area is 8.2. Arc length is what it sounds like. I give you some curve with a starting point and I would like to know if you could, unravel this curve. I am going to assume that it's smooth. How long is it? So if we think of this as a piece of rope laying in the plane, and we could stretch it out flat, how long would it be? Or equivalently, if you were a tiny little dude walking along this graph, tiniest of dudes, and you wanted to walk from the point A comma f of A over here to the point B comma f of B, how far a distance would you have to walk to do that? It's not the same as taking the straight line distance from a comma f of a to b comma f of b, because we go on this wandering like journey through these hills and valleys. The straight line distance would certainly be shorter than the arc length. It turns out that the nicest way to solve this problem is to build a Riemann sum, which will become an integral. So I'm gonna draw this picture a little bit bigger and a little less exaggerated, and I'm gonna kind of show you how you can get started here. Okay. You start by partitioning the interval AB into a bunch of subintervals. You chop it up into n equal length subintervals, just like you do when you're building a Riemann sum to find area at the end of Calc 1. Now maybe I call A x0, and this would be x1, x2, x3, x4, x5, x6, and B here would be x7. So you start by partitioning AB into n equal length subintervals, each of width delta x, where delta x is b minus a over n. And then we consider all these points on the graph at the endpoints of those subintervals. So I call this guy P1, P2, P3, P4, P5, P6, and P7. Each one of these subintervals, I can approximate the length of the curve as a straight line. And I think you can see that as I send n to infinity, the pink is going to become the same as the black. Does everybody get that feeling? The more and more points I use, the closer the pink length will become to the actual length of the curve. Oh, sorry, over here I should label this far left point as P0. So the pink length the approximate length is this pink length. It's the length from P0 to P1 plus the length from P1 to P2 plus the length from P2 to P3 all the way out until you get length Pn minus 1 to Pn. All right, in this case, it would be P6 to P7 is the last one. Now what we're going to do is we're going to find a formula for these things that behaves well as n goes to infinity. But first, let me just write it in sigma notation. This is sigma I from 1 to n of Pi minus 1 to Pi. Is everybody with me so far? Any questions on the sort of setup so far? The nice thing is that since each of these pink lengths is a straight line length, I know how to calculate that. That's the straight line distance from, say, this point to this point. So let's each little length p sub I minus 1 to p sub I is a straight line distance from the point x sub I minus 1, comma, f of x sub I minus 1 to xi, comma, f of xi. Right, like P4 right here is x4, comma, f of x4, and P5 here would be x5, comma, f of x5. And this little pink length is the straight line distance from x4, comma, f of x4 to x5, comma, f of x5. Well, what is that distance? You can use your distance formula. I'll switch back to black. I know this pink is a little tough to read. The distance from, how do we want to do this? AB to C, comma, D is the square root of y2 minus y1. So that would be like D minus B squared plus x2 minus x1. That would be like C minus A squared. So the distance from pi minus 1 to pi is the square root of f of xi minus f of xi minus 1. Let me come back here. We can actually do this more nicely in the delta notation. So if I call this delta yi, and I call this delta xi, the delta xi's are all the same. They're all just delta x. And the delta yi's are the distance from the y value here, the vertical distance, to the y value here. So looking in your distance formula, I'll write it all out, but then we're going to condense it into this notation because it will make things a lot easier to look at. The y values, this is f of xi minus f of xi minus 1 squared plus xi minus xi minus 1 squared which is this difference of y values here. That's delta yi squared plus this difference of x values is just delta x, and it's the same no matter what I is. So that's delta x squared. Therefore, the approximate length is the sum from I equals 1 to n of the square root of delta yi squared plus delta x squared and now there's some funny games we can play. If I force factor out a delta x squared, or maybe, yeah, force factor out a delta x squared, then this will be sum I from 1 to n, square root, open big parentheses, delta yi over delta x squared plus 1 times delta x squared all under my square root. So I'm going to force factor this out. So this piece will become a 1. This piece will be divided by this, and then I can treat that square as being, it's delta yi squared over delta x squared. That's the same as delta yi over delta x all squared. And then here's the guy I factored out. So we're going to force factor delta x squared. And then the last thing I do here is bring that delta x squared, which is now a multiple here, out of the square root as delta x. Because this now looks like a Riemann sum. Delta y over delta x, that becomes dy over dx. That becomes the derivative, dy dx, as n goes to infinity. This becomes dy over dx, or f primed of x, and delta x, I should say becomes, it's not equal to, it becomes that. And delta x becomes dx. So the exact length this becomes the integral for which this is a Riemann sum, which is the integral from a to b, the square root of f primed of x squared plus 1 dx. That's the length of the curve f of x from x equals a to x equals b. This is called the arc-length integral. These integrals are sometimes hard to compute. In fact, they're often very hard to compute. Which is officially why we teach this after teaching power series, because you could bump into these integrals, find them impossible to compute in terms of the old-fashioned techniques, but then rewrite this thing as a series and integrate the series instead. But unofficially, I'm not going to do that to you guys, at least not much. I feel like we've beaten you to death with series enough at this point. So this is the exact length called the arc length of f of x, or that curve from x equals a to x equals b. And it's a formula you should remember. In differential geometry circles and in most textbooks, we give this thing the name S, but I don't think your book does. I don't think your book calls this thing S, so I'll just refer to it as the exact length. So let's use this to calculate some lengths. What do we want to work with? Yes, yes, very good, very good, very good. That's boring, isn't it? Fuck it, we'll do it. All right. So we want to find the length of x to the 3/2 from x equals 1 to x equals 8. So we're going to tuck this formula, this blue formula here in our pocket. All that work we just did was to cook up this blue formula. Now we're going to make use of it. So for our first concrete example here, let's find papers. Humid out this morning. What was it? 2/3, 3/2, 3/2. From x equals 1 to x equals 8. So the graph of x to the 3/2 is this sort of cusp thing. Looks a bit like this. X equals 1 would be like right here. The point is 1, 1. X equals 8 would be out here. 8 to the 3/2. The square root of 8. Yeah, it's not a nice number. 8 to the 2/3 is nice, but 8 to the 3/2 is not. So we're looking for the length of this curve from here to here. It's definitely not a straight line. It's definitely curvy. So if I want to find that length, I do need to use my arc length formula. So our arc length formula says that this would be the integral from 1 to 8, the square root of f primed of x plus 1 dx. So I need to calculate f primed. It's an easy derivative. That's 3/2 times x to the 3/2 minus 1 is 1/2. Oh, sorry, f prime squared. I left off the square here. So this is the integral from 1 to 8, square root of 3/2 x to the 1/2 squared plus 1 dx. Everybody with me so far? Now I can't like distribute the square root. I can't take the square root of this and the square root of this separately. That never works. Square roots and powers in general do not distribute over addition or subtraction. But this square here, I can square this and then try to find a way to sort out an antiderivative. thinking about the stuff we learned back in chapter 7. So 3/2 squared, that's 9/4. So under my square, I'll have 9/4. And then x to the 1/2 squared, that's just x. So we get this. I can't pop the 9/2 out of the square root because it's not a factor of everything in the square root. I don't have a 9/4 here that I can factor out. So he can't come out of the square root again because of the addition. What can I do to solve this integral? Who can help me out here? This isn't a tough one. Yeah, this is a little substitution integral. So here I could let z be everything under the square root, because then dz is just 9/4 dx. I do also need to change my bounds. When x is equal to 1, z will be equal to 9/4 times 1 plus 1, which is 9/4 plus 1, which is 9/4 plus 4/4 is 13/4. And when x is equal to 8, z will be equal to 9/4 times 8 plus 1. So 9/4 times 8, that's 16. That's 9 times 2. 16 plus 1 is 17. So this becomes the integral from 13/4 up to 17 of the square root of z times dz is 9/4 dx. This will be 4/9 dz. And that 4/9 really is a constant multiple now, so it can pop out. And I'm integrating from 13/4 up to 17, the function z to the 1/2 dz. And this is a simple enough integral. You add 1 to the power, divide by the new power. The 4/9 is going to come along for the ride. When you add 1 to 1/2, you get z to the 3/2, and so we need to multiply by 2/3. And then evaluate this whole apparatus from 13/4 up to 17. So the constants can come out. This is 8/27. And then when I evaluate here, I'll have 17 to the 3/2 minus 13/4 to the 3/2. And that's really as nice as this is going to get. I would just leave it like that. 17 is prime, so 17 to the 3/2 has no chance of cleaning up. 13/4 to the 3/2, you can clean it up just a little bit. The 3/2 power of 4 is not bad, that's 8. So that's 13 to the 3/2 divided by 8, but I don't think that really makes it any less opaque. I don't think that makes it any easier to see what the value of this thing is. So I would say, just leave it here. All right, so this is arc length. It's about finding the length of a part of a curve. 17. Yeah, 17 is the bound. All right, when we plug in x equals 8, did I make a mistake here? 9/4 times 8 is 9 times 2 plus 1. 9 times 2. Oh, wait, yeah, 9 times 2 is 18, isn't it? Yeah, not 16. So you're right, this should be a 19. Yeah, good catch. So this is a 19, 19, 19, 19. Good eye, Tanji. Yeah, very good. Thank you. Other questions or comments on this fellow? Tanji was right. When I computed this upper bound, when I changed the bound, I made an arithmetic error. It should be a 19, not a 17. Okay. Let's see. So there are other things we can look at. Working in the setting where x is a function of y isn't especially interesting, so that second example is a little bit boring. What I'd like to do is show you kind of how out of control these integrals can get. I think that is worth looking at least one of. Yeah, so using Simpson's rule. Let's go ahead and set this up for this guy. 1 over x from 1 to 2. So we'll say set up, but do not evaluate. The integral for the length of f of x equals 1 over x from x equals 1 to x equals 2. And I'll draw the picture. We know that in quadrant 1 at least, one over x looks like this. Going from 1, 1 to 2, 1/2. So the length that we're looking for there is the length of this little piece. We know we need f primed. The derivative of 1 over x is negative 1 over x squared. So the exact length is the integral from 1 to 2, square root of f primed squared plus 1 dx, which is the integral from 1 to 2 of the square root of negative 1 over x squared squared plus 1 dx, which is the integral from 1 to 2 of square root 1 over x to the 4 plus 1 dx. And this might not look totally unmanageable. At a glance, this might look like the sort of thing we could handle. Maybe you have a common denominator. That would give you 1 plus x to the 4 upstairs, x squared downstairs, all under the square root. And then if you're feeling fancy, you call that 1 plus x to the 4 upstairs under your square root, and then downstairs here just x outside the square root. If I was going to try to solve this integral, I would want to do some sort of trig sub, I think, right? This x to the 4 is x squared squared. So I might try something like x squared equals tan theta. But then 2x dx would be secant squared theta d theta, and I don't have a 2x to play with. I could maybe multiply by x over x, but this is a tough integral. You could try rewriting it as the integral 1 to 2 x squared down here and an x up here, like this, multiplying by x over x, and then sub x squared equals tan theta, which would be 2x dx equals secant squared theta d theta. But there's all sorts of challenges here. The bounds, for one. Multiplying by x over x gives me the x dx I would need to make the differential work. And this x squared could be a tan theta. But my bounds are going to be tough for a number of reasons, mostly because arctan doesn't get as large as 4. So I really, but the bounds cause problems. No. Inverse tangent of 4 is not a nice number. The bottom bound would become the inverse tangent of 1. So this would be pi over 4 to the inverse tangent of 4. Upstairs here, you'd have the square root of 1 plus x squared squared, which would be the square root of 1 plus tan squared theta. Downstairs here, this x squared would be just a tangent theta. And this x dx would be 1/2 secant squared theta, or secant squared theta over 2 d theta. And I'm not even sure if we can get this done. We might be able to. I'll entertain the idea. But the problem in the textbook asks you to use Simpson's rule, which suggests that it's probably not nice. So if we were stopping the problem, this would be the place to stop. They say set up, but do not evaluate. And then just for fun, I'm seeing if we can evaluate it. That's going to be a secant. So you have secant cubed, 1/2 secant cubed. Because this is going to be secant squared, the square root of which is secant. Secant squared, secant times secant squared is secant cubed theta. And then downstairs here we have our tan theta. I'm not saying this is impossible, but I think it's pretty tricky. Secant cubed is 1 over cos all cubed, and then dividing by tangent, that's the same as multiplying by cosine over sine. So what would we end up with here? 1/2 integral pi over 4, inverse tangent of 4. I've got 3 cosines downstairs, 1 cosine upstairs. So I'll end up with, I'll just write it out, 1 over cos cubed theta times cos theta over sine theta. Oh, this might be manageable. You can cancel one of the cosines. Oh no, but the other sign is downstairs. Yeah, no, this is not going to be simple at all. So you'll have 2 or 1/2 integral pi over 4 to the inverse tangent of 4. 1 over cos squared times 1 over sine. And you could keep working with this from here if you wanted to, but I'm not thinking this is going to go anywhere nice because I don't have the pieces I need to make any sort of substitution. I can write that as cosecant squared, or secant squared times cosecant. Yeah, no, this is tough. So this isn't going anywhere nice. Now again, for the purpose of the exercise, you could stop here because we said we just wanted to set up the integral, not solve it. I just wanted to see what happened if we tried the natural things. And these are the natural things that integral begs this substitution. But even after implementing the substitution, the bounds are difficult. And the integral, while it does simplify a good deal, it doesn't simplify enough for me to have hopes of finding an antiderivative. So look carefully. There was never an x to the 4 in the denominator. I had an x squared here, and it was under this square root. So I took the square root of the top and the square root of the bottom separately. The top just stays the square root of the top, and the square root of x squared in the bottom is just x. So from this line to this line, I had a common denominator. Oh, wait, I see what you're saying. I see what you're saying. Yeah. So this should have been an x to the 4. That's what you're saying, right? Not where did this go, but why didn't this become that? You're right. Yeah, no, again, I made a little mistake here. Sorry. So this should be a 4, which means this should be a 2, which means we didn't need to multiply by the x. But yeah, no, this would be, sorry. So this would be your final answer for this problem. Yeah, that should be an x squared downstairs because this in the previous step here should have been an x to the 4. That's actually going to make this substitution a little bit nicer. Oh no, it's going to make the substitution worse. Yeah, so you could no longer make this go. Yeah, this would no longer work. That's an even worse integral. So this guy, if we wanted to try and solve this, this is still the natural substitution to try and make. But now you really don't have anything that you can use for the differential. When I had it written the way I did before, multiplying by x over x gave me an x here to play with. But as it's written here, if I multiplied by x over x, this would become an x cubed, which I then could not write as a tangent. And so I really am in trouble here. From this point, I'm not aware of any way to attack this integral. So you're correct in saying this x to the 4 downstairs here, when I have a common denominator, should become an x to the 4 here. And then when I take the square root of the top and bottom separately, this will be an x squared. So this is the correct integral. I did make a mistake there. And this integral is actually harder than the one we wrote down a second ago. And this is even worse. The point of this exercise is that arc length integrals get out of control. We can ask for an antiderivative of this just for fun. Well, I don't know if you guys, this number, right, this function here, the 2f1, that's a hypergeometric function. Yeah, it's not the basic Q-basic hypergeometric function. It's a standard hypergeometric function. It's a terrible, terrible thing. You don't want to fuck with it. So this would be as far as we could hope to get. If you wanted to actually know what the length of that curve is beyond saying it happens to be this integral, you would need to then use like a Riemann sum to approximate this integral. You won't be able to find an antiderivative. Or you could try to find a power series for this function and then integrate that series instead. That's another option. But finding a power series for this in the form it's in would be tough. It would probably be a little easier to start here, but even that's going to be ugly. Yeah, good catch, one. Thank you. Sorry about that. So here's the the parts of the problem that would be necessary to answer this question. Set up but do not evaluate. Calculate your derivative, plug into your formula, and then you can simplify as much as you want. This would be an x to the 4, which means after you take the square, this would be an x squared. Okay. So next time, I'm not going to dump this all on you today, but next time we're going to talk about surface areas. So I'm going to open up a new homework for you today. You see here their derivation. They have a little bit of stuff swapping variables and things, but I will give you a few homework problems from 8.1 where you're finding arc length. And then the next section is about surface area. So we're going to take those solids that you guys were finding volumes of at the beginning of the semester and start talking about how to find their surface areas. And it'll be a kind of solid of rotation thing. We're going to be working in a very similar way that we worked with volumes, only now our little differential element is going to be a little differential arc length element. So what you'll see here is that this kind of resembles the volume formulas, only instead of just having a dx, you have this piece here, which is the piece from our arc length formula. So you kind of rotate a little bit of length to get a little bit of area. We're not going to spend a lot of time here. We will do, just like today we did the arc length, we'll do 8.2 quickly. And then we're going to move to chapter 10, where we look at these same sort of problems, but in the setting of parametric curves. And this is actually much more important. So I used to just skip straight to the parametric curve stuff, but I'm hoping that this serves as a gentler introduction. Parametric curves are hugely important in Calc 3, and also in complex analysis and in the right parts of differential equations and a few other places. So talking about curves where instead of giving y as a function of x or x as a function of y, I give you both of them as a function of time. This is a big deal, and I want to get to this reasonably fast. So next time I will teach you the surface area formula. We'll cook it up quickly and then maybe do one example, but then we're going to move on to 10.1. Next week will be 10.1 and 10.2, and the week following will be 10.3 and 10.4, and that's the end of the class. So just to recap here, we do have some holidays coming up. Next Thursday is Thanksgiving, and the school is closed on the following Friday. So next week, we're going to knock out 10.3 and 10.4. Sorry, 10, let's see. So we're going to get to 10.1 this Friday. So we might have to do like a long homework set for the 2 weeks after, because you guys lose a lecture day next Friday. I don't want to try and cram 10.3 and 10.4 both into this week without appropriate time. So this week's homework will be 8.1 and 8.2. And then next week's homework is going to be 10.1 through 10.4, but I'll leave it open for 2 weeks because we have that short week next week for Thanksgiving. Then exam 3 is going to be on the 4th, December 4th. That will be our last midterm exam. And your final, let's double check this for your class, your final exam, this is section 1, right? Yeah, is December 7th at 8 a.m. So I encourage you guys to put these things in your phone right now. Exam 3 is December 4th at 8 a.m., normal class time. And then your final exam is December 7th at 8 a.m., the following Monday. I know that's a little bit rough, but that's just how it goes. So we're going to cover these last few sections, which are fairly easy, over these next 2 weeks. And then on the 4th, you'll have your last midterm. That is the last day of class. And then on the 7th, you'll have your final. Check your schedules. Make sure you don't have any conflicts for the final exam. If you do, please reach out to me as soon as possible so we can get those resolved. The usual rule is if you have a conflict with like biology or chemistry finals, that natural science kind of gives way to mathematics. And they will reschedule their final. If you have a conflict with another class, or if your professor in whatever science class says, no, you have to take this at this time, let me know so I can talk to my department chair and we can reschedule on this end. Any questions for me before we sign out for the day, gang? All right, you're almost there. Just about out of the woods. If you need more time on any of the series homeworks, please submit an extension request in WebAssign. I'm going through and clearing those a few times a day. Otherwise, I will see you guys next time.